I'm gonna need some coffee for this one. It says molten iron at 1538 degrees Celsius, its melting point, is solidified by an ice-water mixture at 0 degrees Celsius. Assuming that there is still ice present when the process is over and the iron is left in the ice water, how much ice will be melted if 50.0 grams of iron is solidified? And we have some information here. So here's sort of what's happening if I were to put it into English. So the heat from iron being solidified at 1538 degrees Celsius and then cooled to 0 degrees Celsius is being transferred, or let's say this, so is being lost. That heat is being gained by ice melting. Being lost or given off that heat is being gained or taken in by ice melting. So that's our process. And what that means is this is a coffee cup calorimeter style question where we're going to have Q over iron equals minus Q over water. And our Q iron will actually have two terms. It'll have one for the freezing, or let's say this, it's molten, which means liquid. So it's going to be going from liquid to solid. So that's going to be delta H, well, we call it fusion. Fusion is when it goes from solid to liquid. That's going to be minus delta H fusion times moles of iron. And then the iron is then cooled, so we need the mass of iron times the specific heat of iron times the delta T of iron. And this is all equal to the minus of the Q, sorry, it's the minus Q water. And what is happening to the water, or ice in this case, is that ice is melting. So the melting process, the minus sign is still there, will be delta H fusion, this time for the ice, or the water, H2O if you will, times moles. And let's see. Yep, we have plenty of information here. Some would say more than we need, but let's plug everything in now. So we have 50 grams of iron, according to our periodic table, which I had at some point around here. Well, we'll fill that in a minute. So embarrassing. Periodic table. No. Molar mass iron. Why does it not give it to me? 55.845. Or 55.85 is what we usually use. So we know our delta H fusion, which is going to be 13.8 kilojoules per mole. I am a joule person, so I will put that in joules. So minus 13,800 joules. My moles, if I have 50 grams and 55.85 grams per mole. 0.895. moles, plus the mass of my iron, 50.0 grams, the specific heat of my iron, specific heat capacity of iron. It doesn't say solid, but this is the value for the solid. It says joules per gram degree or Kelvin. That Kelvin and the degrees Celsius are the same size, so we can use them together, or they can use them interchangeably. And the delta T, final T is going to be 0 degrees, initial T is going to be 1538 degrees Celsius. So now I've got just this left-hand side so far. And since it took up the whole page, why don't I calculate it first? I do note that this part is negative with the negative sign there, and this part is going to be negative with the negative sign there. That's good, because both of these terms should have the same sign. The iron is giving off heat and heat energy in each of or both of these processes. So 13,800 minus times 0.895 plus 50 times 0.449 times 1538 minus. I get minus 46,879.1, which I'll just round to the nearest joule. Still too many sig figs, but we'll go for it for now. That's going to equal minus Q of the ice, which equals minus delta H fusion, which up here, 6.07 kilojoules per mole, minus 6,070 joules per mole. And I apologize, I forgot my joules per mole units up here. And then we get our moles. This will be moles of ice. We had moles of iron over here. And now we can find our moles by dividing these two terms. 46,879 divided by 6070. I get 7.72 moles. And since mole ice is 18.02 grams per mole, I get 139 grams. That's how much ice would melt if we were to cool our newly minted or blacksmithed sword that we had just pounded into shape.